So on page 86, we're going to be finding the third degree Maclaurin polynomial for f of x equals e to the x. So third degree meaning that we have to go out to the third derivative. Now the first, second, third, nth derivatives are all the same for e to the x. All right, so if I want p sub 3 of x, we just have to remember that the a value is equal to 0. All right, so if I evaluate this for when x is equal to 0, I'm going to say f of 0, x equals a equals 0, is going to be e to the 0th, which is 1. F's f to the nth, for lack of a better term, but the nth derivative of f of 0 would also be 1 because it's the same function. All right, so 1 plus 1 over 1 factorial x to the first plus 1 over 2 factorial x to the second. So this is the 0th derivative, first, second, we just need one more, plus 1 over 3 factorial x to the third. I like to take a quick look, like we did with the trig functions in previous pages, just to make sure that we're looking at something that makes sense. So 1 plus x, really the simplified form, plus 1/2 x squared, so I'll write 0.5 x squared, plus it's going to be 1/6, I'm not going to write 0.167, so I'll write it as alpha. I just got to get to my my fraction toolbar jammy here, so it's different on mine, but yours is alpha y equals my free trial for the TI-84 emulator. Took the worst time to expire, but it is what it is. This one's not bad. All right, so I have my two functions here. Hit graph, and it does hold on to the exponential function e for a limited period of time, but it does hold on to it for a period of time, and that's what we care about. All right, so p sub 3 of x, just in case we need the simplified form, is going to be 1 plus x plus 1/2 x squared plus 1/6 x cubed. All right, now it says use your answer to find the limit as x approaches 0 of this. All right, so if we were to say the limit as x approaches 0 of e to the x minus 1 over 2 x, at first glance it would be something that would be indeterminate, which means that there's a limit if you continue. All right, so you would put e to the x in there, you would maybe use L'Hopital's rule, you get e to the x over 2, then you resubstitute, you get 1/2. All right, so let's see how that plays out using the Taylor polynomial, because my answer to part A tells me that this is a reasonable approximation. The p sub 3 of x is a reasonable approximation for f of x. Now, since we're approaching 0, we're talking specifically over that interval. You know, as you look, you can see that it's almost indistinguishable. In fact, it is indistinguishable at that location. All right, because if I replace all of my x's with zeros in the polynomial, I get a 1. If I replace the x with 0 in my original, I also get a 1. So this tells me, or it gives me license to replace the f of x with the 1 plus x plus 1/2 x squared plus 1/6 x cubed minus the 1 that was already there over 2x. The 1s would cancel. All right, we have a common x that can be factored out and canceled. So this is the same as saying the limit as x approaches 0 of 1 plus 1/2 x plus 1/6 x squared all over 2. If I replace all my x's with a 0, so evaluate my expression, I get a 1/2, and that's what we would have expected. So that's really nice. Now, if this limit was going out to infinity, all bets are off, because this is wildly different for large values of x. If I look at the red graph versus the black one. But for the values of x very close to 0, it's very much the same. And in fact, once we get to 0, it's exactly the same. Except the polynomial actually exists there, whereas this, the limit in the e to the x minus 1 over 2x does not. You know, it's an indeterminate expression. All right, so next example, suppose the function f of x is approximated near x equals 0 by a third-degree Taylor polynomial, given. Find the value of f of 0, f prime of 0, f double prime of 0, f triple prime of 0. All right, so since we can approximate it near 0, we have some function f of x that can be approximated by the Taylor polynomial. We can evaluate this using the Taylor polynomial. All right, so what I'm going to do is, instead of finding f of 0, I'm going to find p sub 3 of 0. That's easy enough. That's just a 2. Instead of finding f prime of 0, I'm going to find p sub 3 prime of 0. So I need p sub 3 prime of x. I'm going to leave off the x just so I don't have to write as much. Negative 10x plus 24x squared. That's going to give me a 0. I need the second derivative. So p sub 3 would be negative 10 plus 48x. So plugging in a 0, p sub 3 double prime of 0 would give me a negative 10. And p sub 4, I'm sorry, p sub 3, I think I said p sub 3 in lieu of the derivative. It's second derivative of p sub 3. This one's third derivative of p sub 3. Which is just a clean 48. And so p sub 3's third derivative would also be 48. That's regardless of 0, so I didn't put it in the of 0. So since we're dealing with values that are well approximated by the polynomial function around 0, then if I wanted to evaluate a derivative or series of derivatives around 0, I can. All right, now they're asking, do we have local extrema at 0? One way to do that, because we know again that the function f of x is well approximated by p sub 3, I can type in the function. I can look at the picture. I zoomed in big time here. All right, if I had it as a, you know, like a really outward zoom, it looks like it's kind of leveled off, but there really is, if you bring it in close enough, it does appear anyway that there is a local extreme value at or around 0. So what I would want to do is investigate whether or not there is actually one at 0. Well, I have a critical value at 0, as indicated by the fact that the first derivative of the polynomial is equal to 0. All right? So now it's just a question of whether or not that's truly, if we're doing it or relying on an analytic approach, if that's truly a local max. It appears to be. So what I'll do is I'll take a value that's less than 0 and a value that's greater than 0 and plug it into a sign chart. All right, so my x values, I'll go with something less than 0, 0, and greater than 0. and we'll state what the first derivative is at that location. All right, we know the first derivative of 0 is 0. First derivative at 0 is 0. When we're talking about less than 0, we want something less than but also pretty close to 0. So what I'll do is, well, you can do it a couple of ways. One way would be math. Oh, actually, let me quit out of second mode, get into the home screen. Math. Then we would select option 8, put in the original function, alpha trace y1, the x value, and then something really small and close to 0. So something like negative 0.01. And so we get something positive. That's all I care about, just the sign. All right, then I'm going to do that again. Second enter brings up the previous computation, but this time I'm going to put in a positive 0.01, and that gives me a negative number. So this is increasing, followed by decreasing, and so therefore we're looking at something that is a relative or local maximum. All right. And so that would be a justification. The graph is also a justification if you want to sketch out the graph, copy paste the graph into a digital document.